We're going to take a minute to look at a gravimetric analysis problem that's interesting in its complexity and a little bit unique because most gravimetric analysis problems form a precipitate. You analyze the precipitate to tell you something about the analyte. Here this one's a little bit different in that we have this mixture, the analyte, the thing we're going to analyze, and when we've reacted it with hydrochloric acid, we're going to collect the gas and get moles of the gas. And from moles of a gas, we're going to be able to tell something about our original sample. And that's what gravimetric analysis is all about. So we have a 5.000 gram sample that has 3 potassium salts in it. And part A of this question says, what is the percentage of the potassium carbonate? But then we're going to go on to find the percentage of everything else from this one addition of chemical. So what we're doing here is we're going to add hydrochloric acid. We're adding 100 milliliters, or 0.1 liter, of a 2 mole per liter solution. Now, of course, that's going to react with the with the potassium carbonate, and it's going to bubble out carbon dioxide. And so we're going to dry that carbon dioxide and collect it, and we get 249 milliliters at 293 Kelvin and a pressure just a little less than 1 atmosphere. So using PV equals nRT, we can solve, substituting in those numbers, to get 0.010079 moles of CO2. So this is the reaction that occurred. The hydrochloric acid combined with the potassium carbonate in a ratio of 2:1 and released carbon dioxide and water and potassium chloride. But the thing we're really interested in is for the carbon dioxide, how much carbonate was in the compound, and they occur in a 1:1 ratio. So that allows us to solve for the percentage of potassium carbonate in the mixture. So we have that number of moles that we just calculated of the gas, the ratio of potassium carbonate to carbon dioxide, and the molar mass of potassium carbonate, giving us a mass of 1.393 grams of the potassium carbonate out of the total sample for a percentage of 27.9, because I think we had 3 significant digits earlier on in part of the problem. So now we can go on to find the percentage of everything else in the compound. Now, let's just kind of recap what we've done. We had the analyte, it had these 3 things in it. We added an excess of hydrochloric acid. This produced CO2, but the hydrochloric acid did one other thing as well. There was the potassium hydroxide, and that potassium hydroxide, in fact all of it, was neutralized in this reaction because we knew enough about our analyte to know that we had to add excess hydrochloric acid. And so we have this formula to just remind us of the process that occurred. Now, we had excess of the hydrochloric acid, so we titrated that with sodium hydroxide. So this is how much hydrochloric acid was left after this reaction and this reaction that produced CO2. So now we're testing this just to see how much excess hydrochloric acid there is. So we titrate this with 1.5 molar sodium hydroxide, and it took 86 milliliters, or 0.086 liters. That's how much excess hydrochloric acid there was after the other 2 reactions occurred. So now we should be able to answer the percentage of potassium hydroxide and potassium chloride in the analyte. So let's go on and look at that a little more closely. I started it like this. What I'm doing here is tallying up all the things that hydrochloric acid were used for in this problem. So after the mixture, remember there was the 86 milliliters of base that had a concentration of 1.5 moles per liter. And of course there's 1 mole of HCl for every 1 mole of sodium hydroxide. And that tells me that after both of these reactions occurred, I still had 0.129 moles of hydrochloric acid left. So that's the moles of HCl that I had left. I reacted in the initial reaction with the potassium carbonate. I had this many moles of potassium carbonate, and if you look at the balanced equation, I believe you'll see 2 moles of HCl required for every 1 mole of potassium carbonate. So that's 0.020158 moles reacted. And so those two numbers I know. I know the total amount of acid. Now this goes clear back to the beginning of the problem. There was 100 milliliters of the acid and it was 2 moles per liter. So that gives me 0.2 moles of HCl right at the beginning. And I know I had this much left over and I reacted this much. So if I subtract these from the original amount, it will tell me how much reacted with the potassium hydroxide. So 0.05084 moles of hydrochloric reacted with the potassium hydroxide. So now that I know that, we're going to cause a little major earthquake here, and so here's the number of moles of hydrochloric acid that reacted with the potassium hydroxide. And so I'm going to do the calculation to see how much potassium hydroxide that actually would be. Make sure that's showing up. So 1 mole of potassium hydroxide in the equation here for every mole of HCl. And the molar mass of potassium hydroxide is 56.11. So that comes out to 2.85 grams of potassium hydroxide, and that's 57.1%. So we had an analyte with 3 compounds in it. We've calculated the percentage of 2 of those compounds, so now you can calculate the percentage of the third, because they should all add up to be, yes, you've got it. Good job.